Okay, thank you very much. In particular, I wanted to thank the organizers, Umes, Tomas, Ignacio, and Andy. And I'm going to repeat the first half of Jens' talk now, although he saw my transparencies before. But the second part will be a little different. So I'm going to be talking about quantum simulators, again, this analog quantum simulators, where do we stand? And first of all, I wanted to mention there are very many nice reviews about this subject. This is from 2012, but it's still very actual. A special issue of Nature Physics Inside, actually, I think edited by Peter Soller and Ignacio Cirac. And this is the European Quantum Technologies Roadmap, which is accepted in New Journal of Physics, should appear soon online, because this is only online magazine, edited by Max Riedel and Tommaso Calarco. And here you have a chapter on quantum simulation written by Jens, Immanuel Bloch, me, and Stefan Kur. So the outline is I will start with some kind of ideology, very trivial, but still, since this is not a physics conference, I found it appropriate to say a little about it. I will talk what are the quantum simulators and annihilers. I will talk a little about analog versus digital. What do we want to simulate? I will then go to give you some examples of physics, of some simulations of interesting physical phenomena. Only two, probably, because there is no time. And then the second part will be about errors, validation, and certification. So in a sense, analog to what Jens was presenting, but I hope it will be less controversial. I will not talk about this, but I will be here till Friday, so if anybody wants to discuss this subject, actually, I understand it will be discussed in this workshop anyway. So the ideology. So I will repeat now one of the standard lies, but one of the most famous Californian physicists, but kind of modified. There exist many interesting quantum phenomena, such as superconductivity. These phenomena may have important applications. These phenomena are often difficult to be described and understood with the help of standard computers. So maybe we can use another simpler, better controllable quantum system to simulate, understand, and control these phenomena. This system would be then a quantum computer of special purpose named quantum simulator. Here is your Southern Californian famous physicist. Now, this is a lie, but the important thing that comes from this is that the quantum simulator is really an experimental system that we realize in the laboratory. We theorists, what we want to do with them, quantum simulators, design them, maybe characterize them and formulate the methods of validation, but at the very end we have to convince the experimentalists that they should do it. So how does it work? Superconductors are ideal conductors that conduct electric currents without resistance. This is relatively simple. So obviously they are useful because they conduct strong currents without losses. They would solve if we had them at room temperature, we would solve the energetic problems of mankind. They also have very interesting property that they can generate strong magnetic fields outside of them, but due to the so-called Meissner-Ochsenfeld effect, do not let magnetic fields inside. So if you cool the superconductor below the critical temperature, it pushes out the magnetic fields. This can be used to magnetic levitation, obviously, if you make a magnetic fields by strong magnets around it. And it is used, in fact, to levitate trains nowadays. And unfortunately, as you know, the superconductors exist only at very low temperatures, normally close to absolute zero, but high temperature superconductors at the beginning were at the temperatures close to boiling of liquid nitrogen. Now they are at around minus 100 degrees, but still it's not a room temperature, even in California. So some of theoreticians working in physics believe that there exists a simple model that captures the phenomenon of high TC superconductivity. It's a Hobart model, mentioned many times here. Unfortunately, even this simple model is far too hard to simulate with existing classical computers. So why not try mimic it with atoms? No? So the simple Hobart model is, you can think about it, it's actually a layer of this kind of boxes for eggs. The electrons are like eggs in this box, and they jump from one place to another, and there are two of them in one place. They interact one with another. So jumping or hopping is really tunneling between through the barrier in this periodic potential, because electrons are not only particles, but in quantum mechanics they are also wave packets, so they can really penetrate the barriers, and the interaction is on site. They repulse each other. It is a Coulomb repulsion, but it is screened in the solid state, so it's really short range, only effective there. Trivial in a sense, and in fact the formula that describes this is so long, so the complexity of this formula is close to zero. Still, the model is very complex. So how do we do it with atoms? And we create this periodic potential for the atoms by putting lasers into this kind of, in this case, 3 standing waves. And these standing waves of electric field of the laser form a periodic potential for atoms. So in this figure, you see a 3-dimensional, actually, lattice for the atoms. The balls are not atoms, but are the places in which atoms can sit. Then we load it with cold atoms, with Bose-Einstein condensate normally, so that we have 1 to 5 atoms per side of this lattice, and that's it. And then and these atoms will hop if the potential is not too deep, and also will interact one with another. So it's a perfect realization of the Hobart model. Usually we can do it for the sizes of the order of, I don't know, 30 by 30 by 30, so this order of magnitude of size. In 2D we can do it maybe 100 by 100. So let me tell you another version of this ideology of quantum simulators, which is essentially the same, but now there exist many interesting classical optimization problems, such as, for instance, spin glasses, traveling Seisman, and whatever. And again, they have many important applications, obviously, because many of them are actually NP complete. And therefore, if you, but they are very often very difficult to be described and understood with standard computers. So why not use another simpler and better controllable quantum system to solve or to get information about the solution of these problems? Okay, this is really the ideology on which the wave computers wave. And such system we would thus work also quantum simulator. That would be a quantum computer of special purpose. But nowadays they are often called quantum annealers because they use quantum annealing as a method of solving these problems. Or maybe even more exactly, they use something like adiabatic computing, going from one easy state to the solution of the problem adiabatically. Again, famous Californian. Okay. What about the analog or the digital? In principle, this ideology that I presented, of course, allows to be either analog or digital. In the digital case, you have error corrections and all the things that you have associated with gates and things like that. In the case of analog, there is no error correction, so there are more questions concerning validation and so on. What shall we simulate? This has been already said by Jens. Statics at 0 temperature, so ground state and its properties. Statics or equilibrium dynamics at non-zero temperature. I mean, these two things are very important because they will tell you where and at which parameters we have quantum phase transitions to interesting states like superconductivity. But similarly as in Martin's talk, we don't really care so much about the value of the ground state energy. What is really very important thing for us is to find the parameters, the knobs, which we can turn in order to increase, for instance, critical temperature for superconductivity. This is the very important thing. So it's like in chemistry, the differences between energies, which are important for us, more than absolute values in these simulations. We would like to simulate, of course, dynamics out of equilibrium, which also was mentioned by Jens, and dissipative dynamics. So I will go through platforms slowly again, so that you remember more. The most developed platforms are ultra-cold atoms in traps. Pardon?
What is the signature of the high DC superconductivity? If I manage to simulate the Hamiltonian, what do I see in order to see the high DC superconductivity?
I mean, normally superconductor means transport. So the best thing is to do in solid state you would do the measurements of the currents. Okay. In atoms it is not so easy, but also you can do it nowadays. There are methods to do it. Okay. But there is other things. There are correlations and things like that, which characterize this. In a sense, you can think about the superconductor as a condensation of kind of pairs, which is not completely true, because in strongly correlated regime, it doesn't apply this system. But then it's like a Bose-Einstein condensate between the space, so there is a phase coherence between them. Okay? And this can be measured even in this opening the trap and this time of flight thing. Sorry. The first thing which was first, so to say, was ultra-cold atoms in traps, not even in lattices, or on chips. All right? They realized quantum field theory with 5 to the 4 interactions, or even more model if you have longer interactions between the atoms. So, for instance, dipolar forces or something like that. So here I show you a picture from the papers of the group of Christophe Salomon in Paris and the group of Martin Zwirlein at MIT, presenting the phase diagram of the Fermi, ultra-cold Fermi gas, 2-component Fermi gas. So you can think spin 1/2 fermions. And this is a phase diagram. The pressure as a function, this is at 0 temperature as a function of so-called Fermi momentum times scattering length, which measures the strength of interaction of the fermions, and here chemical potential in units of temperature. So this is in the regime of parameters in which there is a phenomenon called BCS-BEC crossover. On one hand side, when the interactions are weakly attractive, the electrons attract them. Electrons, in this case, are atoms which mimic electrons. They attract each other and they form the Cooper pairs. But these Cooper pairs are huge in space, but they are localized in momentum space. Okay? On the other side here, the effective interaction scattering length is positive, so they repulse each other, but there exist molecular states which have very, very small negative energy, and they form these molecules which are now localized in space, and these molecules condense into Bose-Einstein condensate. In the middle, interactions are infinite. And it is very, very difficult to describe. Of course, on these pictures, you see some comparison with the Monte Carlo diffusion Monte Carlo mostly simulations. But really, in the regime of these very strong interactions, there is still a lot of open questions for imbalance system and so on, in which the computers do not give us the answer. Ultra-cold atoms in optical lattices. So here we can do Hobart models in particular, and also spin models. This is a photo from Immanuel Bloch seminal experiment in which, for the first time, this microscope for atoms was realized, in which they can show that they can see individual atoms, essentially. They have access to seeing individual atoms. So here, this is how the superfluid state look like. This is a Bose-Hobart model now. So these are bosons which form condensate. This is a condensate. This is when these bosons form a so-called Mott insulator. There is exactly 1 atom per side. And this is also Mott insulator in which you have more atoms. So in the middle of the trap, there are 2 atoms per side, 1 atom per side, and then nothing. 2 atoms they cannot detect because detection method is such that they can only distinction between even and not. Doesn't matter. There is a book about it, which we wrote, I think, published in 2012, but in last year there was a paperback edition, so you can get it maybe below $50 nowadays, and it's corrected on top of that. Next platform, trapped ions, was also mentioned by Jens. So the ions have 2 internal states which serve as a qubit, ground and excited. It is easy to monitor whether the ion is in the ground state, because you can look at the fluorescence to the side level, and this is I would say 100% nearly efficiency of checking. These ions interact with phonons, and through the phonons you can realize gates. The most known is, of course, Dirac-Soller gate, and this is a very nice system for quantum simulations. Although, and this is an example of quantum simulations of the Hamiltonian, which is this kind of easing in transverse field for, I think, 4 spins, And this is the more exotic Hamiltonian with 6 spin interaction, both done in the group of Reiner Blatt. So here time is, of course, you apply these gates many, many times, but you can do it with very good fidelity. You can also do it in analog manner. Okay, next one is circuit QED. Here what is happening is that you have small microwave cavities in which there can be microwave photons, and there is superconducting qubit inside. And this realizes the famous model of quantum electrodynamics, so-called James-Cummings model, interaction of two-level atom with a single mode of radiation. And these cavities can interact one with another because the photons can tunnel from one place to another. That's why this kind of simulations are called simulation of cavity QED. Josephson superconducting qubits or arrays of those, which can simulate, for instance, using spin glasses, and you know what it is. And finally, photonic platforms, which were also mentioned today. Usually you have in photonic platforms, you usually have photons on the input. They go through some set of waveguides. They can tunnel from one waveguide to another, and then you sample at the end. The boosting to this kind of tech platform was actually caused by the paper by Scott, in which he showed that at some situation you can, from this measurement, get information about the NP hard problem, which is a calculation of permanent of the corresponding, I would say, transmission matrix for this system. So I show you 2 interesting systems that was reported this year. One is for ultra-cold gases in the trap. In this case, it's in fact a mixture of 2 kinds of bosons which attract each other. So normally, if there would be a standard mean field theory applied to describe this system, they would collapse, okay? Because they attract each other. However, there are quantum effects beyond mean field, which is essentially the 0-point fluctuations of energy, which depend on the density of these guys. And this 0-point fluctuations stabilize the system so that they can form what people call quantum droplets, because these are the things that are similar to helium droplets. They have higher density than BEC, and they are very different. So I show you the experiment has been done actually in ICFO in my institute and by my colleague Laetitia Taruel. And here, maybe look at this picture. This is when the interaction, you can control the interaction between these bosons. If this interaction is repulsive, then if you have the cloud of these bosons in the trap and you open the trap, well, they spread, yeah, because nothing keeps them in the place. They diffuse. If the interaction is too attractive, then this collapse occurs. You open the trap, but they don't go away, but they collapse into something very small. And then in the intermediate situation, when the interactions are not so negative, not so attractive, if you open the trap, the thing stays there and forms this droplet of high density. Again, there are some simulations, Monte Carlo, for this system, but it's absolutely not yet clear whether these systems are superfluid, what are the properties, and so on. And most probably this will not be easy to simulate in the normal computers with precision, because it is really strongly correlated system. Okay, another example is the famous cold atom Fermi Hobart model. This is from Markus Greiner group from last year. So this is really studying, again, high TC superconductivity. So this is the figure that I think Jens shown. So you can see this is what we expect the phase diagram of the system is. You have antiferromagnet here when you assume here that the total, when the number of atoms or electrons per site is exactly 1, you are here in the antiferromagnetic phase. If you start taking these atoms away and you have less atoms than sites, then you enter strange phases, so-called pseudo-gap phase or strange metal phase. Fermi liquid, this is relatively normal phase, but still. And the D-wave superconductor, this is what we believe. Greiner, in this paper that was reported last year, was able to go with his system on this line from the Mott insulator to the antiferromagnetic order, and then into the phase of this strange metal. So this is how the pictures with this single atom microscope views look like. This is when he is at this point, and then you see that you start to see this kind of checkerboard here, which means that he takes out one spin component, and what is left should look like a checkerboard pattern expressing the ferromagnetic order. Now there are much more advanced experiments in which he has reached even lower temperatures and entropies, but I have no time to talk about it. Let me talk a little about this errors validation and how I'm doing on time.
You have about 5 more minutes.
Okay, so first thing you would like to maybe measure or optimize is energy or cost functions with these things. Of course, this can be also a very hard problem to compute. But as I'm saying, in a sense, you can maybe go to smaller systems and use variational upper bounds using tensor networks and things like that. You have some control on the error here. You can use finite size scaling to see how it goes. There is also an interesting idea that there are semi-definite programming methods for the lower bounds of the energy. I mean, this was pioneered by Tony Assin in these papers on which they really based it on the characterization of the correlations in quantum systems. And there is in particular also, the pioneering work was in 2008, but this is more, is longer and has more information. And there is also a nice paper by Tilman Baumgartz and Martin Pleniok, where they explicitly construct methods to calculate lower bounds for energy. Validation. What does it mean, validation? Well, validation means go to parameters regime where the classical simulations are efficient. So what can it be? Suppose that you want to do frustrated system, all right? So in the frustrated system, very often Monte Carlo doesn't work because there is a sign problem. So you go to low frustration, and maybe there Monte Carlo works or works better. You check it there, and then you go to the regime of parameters in which you don't know. It's terra incognita. But this is the same with the normal classical computers. Of course, you have more methods of checking convergence and so on. But here also you can check how when you repeat the experiment, you should get the same results and things like that. Another possibility is always go to small system where you can always do simulation classically and use finite size scaling. So this is a seminal paper from the Immanuel Bloch group, where they take again this Bose-Hobart model, and they compare it with the best of the best, the creme de la creme of Monte Carlo simulations and Monte Carlo simulators men. Simulator men, okay, Lode Paulette, Nikolai Prokofiev, Boris Svistunov, and Matthias Treuer. So here is the ideal phase diagram of this Bose-Hobart model, and here are comparisons between the numerical Monte Carlo simulation and the experiment, which are perfect. Okay, they even did it for time of flight pictures. So they open the trap, they let the thing go. If this is super fluid, they see this kind of nice interference Bragg peaks. And in the Mott phase, they see this kind of fuzzy things, and this is the simulation. So everything is fine here because Monte Carlo is working for this kind of system. There is no problem. But of course, if you would go to bigger system, then in order to make comparison, you would have to buy a new computer for a couple of $1 million. So in this sense, it is a good simulator, the experimental system, I mean. And finally, robustness. What we meant by this robustness is that one of the things that you can do in these experiments is you really can add perturbations in a controlled way. So disorder or noise, time dependent. And you can check how sensitive you are. And this gives you information how well you have to determine your constants in the Hamiltonian to get what you want really to get. Okay, so like in the chemistry, they told us 1/1000 NZ. So here you can also check it to some extent. And we wrote a paper about it, a review in a couple of years in Reports on Progress in Physics. And the example that I show here is a one-dimensional system. Everything can be, of course, calculated here. But we look at the correlation length, which is in these colors, at the critical point of the transverse field easing model. And we check how does it decreases with growing disorder, and also how the critical temperature, this is this line, actually increases with the growing disorder. Okay, and in a sense, this is the way of calculating this sensitivity. All right. Finally, certification. This is more modern term. You can certify entanglement or certify even non-locality in these systems. And this is more or less answering the following question. Very often we expect that the ground state of the system, or even we want to prepare the ground state of the system such that it is entangled. And how can we be sure about it? In this kind of annealers things, we can ask, is this device really quantum computer or simulator or not? Are the results correct? And things like that. So the new methods for this kind of certification are being proposed in the recent years, and I will show you few. This is first of all, we can measure something. This is the first measurement of entanglement entropy, again by the Marcus Greiner group. The method which was proposed by Dieter Jacks many years ago. He has a system, divides into two, and he measures the swap operator on the half of the system. So he makes two copies and makes a swap operator on the copies. Very complicated experiment. But hopefully, and of course what he measures in this way is the Renai entropy of the order 2. But sooner, in last year, I think there was, no, in this year actually, published was this beautiful paper by Sirac and Zoller, in which they show that you can measure this Renai entropies if you apply random unitaries to your reduced density matrix. You measure this kind of projection on a state in a given basis, and you average this probability distribution. If you calculate this average over the random unitaries, then, for instance, for p-squared, you get directly the Renai entropy. Now, how do you realize random unitaries? This is what the paper is about. You do it with some random quenches. The method is shown, and it is validated, that it works quite well. And this method actually was used, this or very similar method were used by Marcus Greiner to study entanglement in the many-body localization problem, but I have no time to talk about it. The one that I want, two more papers that I want to mention is one is efficient device-independent entanglement detection by multipartite systems, which is by Tony Asin group. What they have is they build hierarchy of the sets that limit the local, the set of local correlations, so the ones that do not break Bell inequalities, from outside. We know that the quantum sticks out somewhere here. So at some moment, the sets, which are relatively easy to characterize, will, if we get a kind of Bell inequality touching this set, we will also have a witness of entanglement. This is more or less the idea. The other thing that we can also do, and this we did already in 2014, we proposed how to detect non-locality in many-body systems. So we do it with Bell inequalities which involve only two-body correlators. That's why it is possible to characterize this kind of Bell inequalities. Actually, we have characterized all of them for the case when they are symmetric with respect to permutations of the particles. And this is a very nice method because it will also allow for the device-independent witnessing of many-body entangled even. So here in the figure I show you, the more you violate this Bell inequality, the deeper you are in this region, because this is quantum forbidden region. If you are below of one of these blue lines, then you can be sure that your system is more than K producible. K producibility is that you can produce a state with the clusters of K particles and things like that. So you have test of many-body entanglement here. And the last figure that I wanted to show, this is another way of presenting the same diagram. This is how deeply you violate this inequality. This is some parameter of the system that they were measuring. And this is experimental result, actually, from the Basel group, which they obtained the result that they can be sure that they measured the entanglement with 32 producibility. So at least 32 guys are generically entangled in this system. And with this, I finish. My conclusion is usually enjoy physics and beyond, but here is different.
Go ahead.
Yes, I'm sorry, it's a bad question, but I think
There are no bad questions.
I think connect the dots between like well inequality violations and quantum simulations. So how what is the logical connection? How should I think about this?
Okay, I would rather say that one thing is the quantum simulation where you want to prepare interesting states, in particular the states which are strongly correlated. And in these states you would expect that you would have a lot of entanglement. So you want to certify it. And how do you certify entanglement in many-body systems? I mean, these are the papers which try to propose the experimentally feasible methods of measuring entanglement and even non-locality in these many-body systems. I think that this is what I can tell you. The relation is that this is a certification tool, that what you do is correct. It's not related to simulation itself, but when you simulate, you want to know that at the end you have created something interesting. So you measure many-body entanglement, for instance. Okay, this is the only thing. It's a diagnostic tool.
You know, I'd like to ask something. You showed a picture of the D-Wave machine, but last year D-Wave claimed that they could map an 8 by 8 by 8 group of spins into their machine. They varied the magnetic field, and they measured critical exponents. And, you know, so they turned it into a machine for physical simulation. And I wonder how, you know, you were listing all these different people who did, or groups that did this. You didn't include that experiment. Are you aware of it?
I mean, still, as I know, I'm not aware of quantum simulation time-dependent. I always thought that they are doing some optimization problems which are classical. I never heard that they use the quantum.
I'm telling you, last year they mapped an 8 by 8 by 8 group of cubic lattice into the machine, varied the magnetic field, and measured critical exponents. And so, you know, there was a device with 512 qubits. I can't judge if it was.
I can judge neither because I don't even know. I saw him in November.
Harris?
Yeah.
That's the guy who spoke about it.
I saw them, no, even in February. But they mostly, I mean, in February they mostly talked about what they did before, which was the easing, classical easing, and about the machine learning relation and the fact that they can sometimes do better way of optimizing the back propagation thing. These are the things, but I never heard about this. But
Yeah, no, I think they did actually. It's a pretty nice, it's a pretty beautiful quantum simulation. They compared to kind of Monte Carlo and got out sort of the right exponents, and I think that.
But exponent for the quantum phase transition?
Yeah. Is it quantum? Was it quantum actually?
I think it's classical, everything that they do.
Well, that was maybe the classical exponents, maybe.
I think they have actually, I think it's not so easy to reach, for example, quantum critical region in this.
Yeah, because
I think that it's hard to believe. I think what they could have done three-dimensional easing. No, but even that, it will be very difficult. Probably they could do three-dimensional easing in magnetic field, uniform, and they can look for the transition there, and then to calculate the exponents. This I can imagine. But for the quantum,
I think
I would be skeptical.
I mean, it is actually a very nice work, but there are two problems, you know, and I think there are two papers, which I don't know which one is, but one of them is, as far as I understand, was the temperature was just not low enough to really reach this quantum critical regime. And the second problem is that the system is fundamentally strongly coupled to the environment. And once you are in this kind of quantum critical regime, this coupling to environment certainly plays a role. So, and that's why I think it's not, like, I'm not sure that this
I will check. I will check. I will check tonight and tomorrow. If anybody wants to discuss, I'm ready to do that.
That was just, in the list of things.
Yes, yes.
Okay, any more questions? Okay, so I think, are we done for the day? Who's the boss? Okay, thank you. Thanks again.